Hydroxide ion is a strong base. It can be consumed in the body with a weak acid, such as dihydrogen phosphate ion produced in the kidney. In the reaction, an H+ ion transfers from the acid to the hydroxide ion to form water and HPO4 2- ion, the weak conjugate base of the weak acid.
I used to have a friend that did research, and she would go down to the Caribbean and find different kinds of sea life solutions, like blood or whatever. I don't know what they were. I don't do anything biology. But anyway, she would then scuba dive to get these. Oh, I was jealous. But anyway, she'd come back and then analyze all these new weak acids using these kind of processes. And that was her research. And that's so cool. I still think that's a pretty neat thing. But anyway, I digress. I did things that were dead and stuff. But anyway, that's a personal problem. Nothing you need to worry about. This is an example of a weak acid plus strong base titration, and there are a couple of things that are different here, and it's worth talking about. So we'll begin. The first thing listed is what you start with. So we're going to start with a weak acid here, and then we're going to slowly add a strong base. And like before, we're going to have regions. We're going to have an initial region. We're going to have an equivalence region. There's going to be a pre-equivalence and a post-equivalence region. And again, those are all based on moles. So initially, we'll have only the moles of weak acid, NWA. At equivalence, the moles of weak acid and moles of strong base will be equal. Pre-equivalence, we have more moles of weak acid than strong base, and the post-equivalence means more strong base than weak acid. And we'll have different equations for that. Now, one thing that's really cool, though, about weak acids is you need to know the Ka. And we're going to see here in a little bit that the half equivalence point allows you to find pKa from pH. The half equivalence point is literally half the volume or half the moles needed to reach equivalence. So in this case, it looks like it took 25 milliliters to get to equivalence. That means 12.5, which is right about there. That's the volume of half equivalence. And if you go up and over to the pH right there, that pH is going to equal pKa. And this is an awesome way to find the Ka for an acid if you don't know what it is. Pretty powerful. If you have a weak acid and strong base, at equivalence, the strong base moles and the weak acid moles have canceled each other out. However, at equivalence, if they're both wiped out, the weak acid has turned into its conjugate base, and base is the operative word. So notice that the equivalence point for a weak acid strong base titration will be basic. It'll be greater than 7. So for this particular problem, it looks like the pH is close to about 9. That's a basic way. So if you don't know if your acid is strong or weak, do a titration. If the equivalence point is greater than 7, you've got a weak acid, which is by far more common than a strong acid, which should give you an equivalence point pH of about 7. The pre-equivalence region will act like a buffer. We can actually use the Henderson-Hasselbalch region equation in there to describe the pH of this buffer system. So you can see right in here, the pH change is pretty gradual. That's going to be a buffer region. HH equation to the rescue. Big surprise. I love the HH equation. I'll use it anytime I want. It also explains why at half equivalence, pH and pKa are the same. Because if the moles of base are half of the acid, that's going to get you to half equivalence, and pH equals pKa. So just to highlight that last part, if you have a weak acid and strong base titration and you're at equivalence, what will the pH be? And again, at equivalence, the weak acid and strong base moles are equal. They've wiped each other out. However, the weak acid creates its conjugate base, and bases will be basic. That means the pH should be greater than 7. And this is what you see when you have a weak acid and strong base titration, all right? The annihilation of the strong base has destroyed the weak acid, but the weak acid has kind of a surprise left in it. It comes back as a conjugate base, and it's a weak base, but it's basic. pH should be greater than 7. So you can find equations, and we're not going to go through this in great detail. A weak acid pH is minus log square root Ka times Ca, as long as 100 times K is less than C, which it almost always is. So this is a great way to find the initial point pH. Now at pre-equivalence, we're going to use a variant of the mole version when you had a strong base on a buffer, because in the pre-equivalence region, not only do you have the weak acid, but you're starting to make the weak conjugate base as well. So when you do the math, and you don't have to worry about it, pH equals pK plus log the moles of strong base divided by moles of weak acid minus moles of strong base. And so it's pretty cool. You don't have to worry about the volume, but you do need pKa, stuff like that. At equivalence, you have only the conjugate base left over. This is the ugliest equation. However, it's not so bad if you remember that a weak base, pH equals 14 plus log square root Kb times Cb. Now, Kb equals Kw divided by Ka. And probably you were already using Ka, for example, up here in the initial point. So Kw divided by Ka equals Kb, but if you have Kb, you can put that in there. And then the concentration of the base, all the weak acid has now turned into conjugate base, so the moles of weak acid will equal the moles of your conjugate base, and you just need to divide by the total volume. And then finally, at post-equivalence, you have a strong base left over. This looks a lot like the post-equivalence for strong acid, strong base, except instead of subtracting moles of strong acid, you're subtracting moles of weak acid, and of course adding volume of weak acid instead of weak volume of strong acid. But very similar. That's where the strong base dominates, and you're good to go. Differences in titration curves can occur. So strong acids tend to have very sharp equivalence points. So you can see there on the left graph there, that S-curve is very, very sharp. On the other hand, with the weak acids, they're a little bit more gradual. They will depend on the Ka. And as the Kas get smaller and smaller, those S-curves become more like straight curves all the time, which is crazy. Now, also, I wanted to point out how those half equivalent points are really important for weak acids. That's where pH and pK are the same. So for example, on the graph on the right, which is a weak acid, it looks like 25 milliliters is the equivalence point, 12.5 kind of right there in the middle, that would be the half equivalence. So for this problem, it looks like the pH will be close to 5, and you could do a better job than I could do on my lame iPad here. But anyway, whatever that pH is, that's going to equal your pKa, and then 10 to the minus pKa gives you Ka. So this is an awesome way to find Ka from a graph, which is really cool. But you can also see from the curves there that there are differences and stuff from all that. Good to go. Polyprotic acid will also have a different kind of curve. Now this is for phosphorus acid, and you can see here how there's like two S curves. There's one right here, and there's a second one right there. So the first S curve is when the first H plus pops off. And if you want to find pKa1, if you will, you can go back half the volume to that little X right there. That pH is going to equal your pKa1. However, because we have a second equivalence point, you can see it's right there, you can also find the second half equivalence. And that's going to be halfway between the two equivalence points at that little X right there. And there, that's where pH and pKa2 will be the same. So it's kind of a cool concept, really neat. Sometimes it's difficult to find the third equivalence point. It can be done, but you need some special techniques. We don't need to worry about it, but if polyprotic acids, you can absolutely find Kas and all that same kind of stuff too. Pretty awesome. An indicator can be used when you don't have a pH meter. pH meters are always the way to go. However, indicators can be useful too. An indicator is nothing more than a chemical that changes color under certain pH ranges. So on the right-hand side there, you can see that bromothymol blue. If you have an acidic pH that's less than 6, it'll be kind of a yellow. It's kind of a green in the middle, but greater than 7.5, it actually becomes kind of blue. So it's kind of a cool concept and stuff that can be used. And before the advent of electronics, they used a lot more indicators than they do now. Now this table on the left here shows different indicators that are possible, and there are thousands of indicators. Bromothymol blue is right there. You can see it's yellow kind of to the left there, about 6, kind of green in the middle, roughly 6 to 7, and roughly 7.5 or so is where it turns blue. Phenolphthalein, which is right here, is a common indicator used. It turns red when you get a lot of base around. So in acidic solutions, it's colorless and it turns kind of a red-pink color when it's around a base. So they're kind of helpful, but they're not as cool as pH meters, especially if you want to measure quantities like find equivalence volumes and pHs, stuff like that. Here's a question where you might want to think about which indicator would be best. And indicators should be kind of calibrated to your equivalence points. So we have here two possibilities. Phenolphthalein, which is on the top right here, and then on the bottom part here we have methyl red, and the question is which one would you want to use. So you can see here that there's like a blue kind of a graph right there, and the blue graph has a steep point, i.e. the equivalence, that's right there, all right? And notice how that's right where the methyl red begins to turn kind of a yellow into more of a red color. So in this example, I would absolutely say that because the equivalence point is at a pH less than 7, you want the color change to occur less than 7 as well. So methyl red would be a much better choice here. Phenolphthalein up until about 8 is a colorless solution, and past 8 it would begin to get kind of a red-pink color. But before 8 it would just look colorless, and that wouldn't be very helpful for our equation right here because we want the equivalence point to reflect itself in the indicator color change. So definitely methyl red would be the better color here.